In this video, we're going to continue on with our discussion of section 3.1, higher order linear differential equations. Here, we're going to talk about the Wronskian next. And so first, we're going to define what that is. And then over the next few examples, we will start to see why that is important and how that is related to solving nth order linear differential equations. So first, let's suppose that each of the functions f1, f sub 1 of t, f sub 2 of t, all the way to f sub n of t, all possess at least n minus 1 derivatives. And we say the determinant of this matrix is called the Wronskian of these functions. What is this? Well, we just put all of the original equations up in the first row. We place all of their derivatives in the second row, but make sure that we line it up where f sub 1 is in the first column and f sub 2 is all in the second column, and we don't mix those up. And so on. So our third row is the second derivative, and all the way down to the nth row being the n minus first derivative. So if we place that, then that matrix is called the Wronskian of these functions. Sorry, the determinant is the Wronskian of those functions, the determinant of that matrix. So we say that these functions, f1 through f sub n, are all called fundamental if the Wronskian is not equal to 0, i.e. the determinant of this matrix up here is non-zero. All right, and now we're going to take a look at why that is important. Actually, we'll take a look at why that is important in just a moment. First thing we want to do is just see if we can determine when two functions form a fundamental set. We're going to determine whether the following functions form a fundamental set or not. So the first thing here is to calculate the Wronskian of cosine of t, sine of t. So we're going to find the Wronskian of this. Well, what is that? That is the determinant of some matrix here where we put cosine of t, then sine of t, and then in the second row we place their derivatives. So the derivative of cosine of t is negative sine of t, and derivative of sine of t is cosine of t. We want to find the determinant of this. Well, this is cosine squared minus negative sine squared, which is cosine squared plus sine squared, which is 1, which is not equal to 0. So this, in fact, does form a fundamental set. So cosine of t and sine of t do, in fact, form a fundamental set. All right, let's try this for sine of t and 2 sine of t. So we find the Wronskian of sine of t, 2 sine of t. This is the determinant of the matrix sine of t, 2 sine of t, and then derivative of sine of t is cosine of t. Derivative of 2 sine of t is 2 cosine of t. All right, so then we get 2 cosine of t sine of t minus 2 cosine of t sine of t. Well, that is in fact equal to 0. So these do not form a fundamental set. Okay, so that was just some practice in determining if we can find out if a set of functions form a fundamental set. Now we get to discuss how that's related to solving nth order differential equations. And that is because of this following theorem. If we have n solutions here of an nth order linear differential equation, notice that those n values are that n value is the same. So we have the same number of solutions as the order of the linear differential equation. And if we take all of those solutions and they form a fundamental set, then the general solution is just a linear differential equation. Is a linear equation with those in solutions. So x is equal to, so we have a solution x here, and that is equal to the sum of x1, x2, when each of those is multiplied by an arbitrary constant. And that gives us our general solution. So we can let these C1, C2s be any arbitrary constant, and this sum will be a solution. And in fact, that is the general solution because all of our solutions will be of this form. Again, what is our assumption here though? Our assumption is that x1, x2, all the way through xn are all solutions originally, and they form a fundamental set, i.e. when we take the determinant of that matrix, we find that that determinant is non-zero, where the matrix is defined as above that we discussed earlier. Okay. So we're going to do an example here. And we are going to find the general solution of the differential equation x double prime minus x equal to 0. We've already found some solutions here. We noticed that x of t equal to e to the t is a solution. And we also noticed that x of t equal to e to the negative t was a solution. Now, do those two functions form a fundamental set? Well, we can verify this by finding the Wronskian, which is the determinant of this matrix. Right? We write our one function, we write our other function here, and then we take the derivative right of the first function, write it there, the derivative of the second function, and put it there. And then we calculate this determinant. This is negative e to the negative t times e to the t minus e to the t times e to the negative t. Well, that is negative 1 minus 1, which is negative 2. And since that is not 0, in fact, this tells us that e to the t and e to the negative t form a fundamental set of solutions. Then, since this is a second order linear differential equations, we have two solutions. Then our general solution is just the linear combination of these two functions. And this is our general solution to the linear differential equation x double prime minus x is equal to 0. All right. We have one more example that we'll do in this video, and that is to find the general solution of the following differential equations. We have two parts here, A and B. So we're going to do part A first. Notice that we have, okay, so we have this function, x double prime plus x is equal to 0. Notice that if x is equal to cosine of t, then x double prime is equal to negative cosine of t. And so we get negative cosine of t plus cosine of t is certainly equal to 0. So cosine of t is a solution to this differential equation. Similarly, we can see that sine of t is also a solution. So we have two solutions to our differential equation. Then I would like us to recall that in example 3, we showed that cosine of t and sine of t form a fundamental set. So, since cosine of t and sine of t both form a fundamental set, and they are solutions to this linear differential equation, that tells us the linear combination of those two solutions is our general solution to this differential equation. What does that mean? That means that all solutions to this linear differential equation are of this form here. And that solves our linear differential equation. X double prime plus x is equal to 0. All right, now we're going to solve this one. And we'll talk about two different methods here. First one is we can just use successive antiderivatives. If x triple prime is equal to 0, then x double prime is some constant c1. X prime then is c1t plus c2. And x triple, then x is c1t squared over 2 plus c2t plus c3. And so our solution, some constant times t squared plus some constant times t plus c3 plus some constant, is a general solution to this. And that should make sense. Anything of this form, when we take the third derivative, we will get 0. Okay, we're going to have one more method for the solution, and we're going to use our Wronskian for that. So our second method for solution is to observe that x1 equal to 1, x sub 2 equal to t, and x sub 3 equal to t squared all satisfy this linear differential equation. Then notice that the Wronskian of those functions is the determinant of the matrix. To get the next row, we need to take the derivative here. So the derivative of 1 is 0, the derivative of t is 1, the derivative of t squared is 2t. And the third row is the derivative of the previous row. So we get 0, 0, 2. And we find a determinant of this. You can find a determinant of that as normal. Or if you've taken a linear algebra, you can recognize that in an upper triangular matrix, the determinant is just the product of everything along the diagonal. So this is 2. So our determinant is 2 here, which is non-zero. This tells us that these three functions form a fundamental set. If those three functions form a fundamental set, then our general solution is just a linear combination of those three solutions. And this is our general solution to this linear differential equation. All right, and that'll conclude this video.